Our first speaker this morning is the author of two great books. One is Learning Domain-Driven Design, and he published this during COVID, so I guess he didn't have a lot of work then. And then the second one was Balancing Coupling in Software Design, which he published in September of 2024. He told me this was 3 years behind schedule, which proves that he's a real software engineer. This is his words. He's been a software architect for over 15 years. And I added this a little bit. Because he didn't want to tell me, he designs a lot of secret stuff. So maybe you can get it out of him at the end. And I asked all my presenters to tell me one interesting thing about themselves that we might not know. He's not a cat woman, he's a cat man. He has 5 cats. Maybe he'll tell you why. Let's give a great big welcome for Vlad Khononov on stage. And where is the title of your speech? Where is the title of your speech?
It's here.
The Fractal Geometry of Software Design. Good luck.
Thank you. Look, I really hope you had your coffee this morning because stuff is about to get heavy with this talk. And also, Slido, forget about it. We are not going to have any time for that, but you can catch me during one of the breaks or during lunchtime. Okay, so if you read the Monkey book, you're awesome. If not, nobody's perfect. You know what to do. This one, Balancing Coupling, is finally published. Can't believe I'm saying this. Every time I'm saying that it was published last year, still feels like a dream. My goal was in that book to systemize knowledge of our field of software engineering that we accumulated since 1960s and to this day. And some of that knowledge has been forgotten already, so I'm trying to remind you about it. And also, some of it is a bit non-trivial to implement nowadays, so I'm adapting it to our current world. That book is based on lots of other books, and one book that really changed the way I'm thinking about software design is this one, Scale. And what's special about it is that it has nothing to do about software design. This is a book about biology, social sciences, and most importantly, it's about complex adaptive systems. Its author, Professor Jeffrey West, starts the book with some peculiar observations. He says, let's take a few quantities that play very important roles in our lives, such as how much food do we need, how creative are we, and how profitable are our companies, and plot these quantities against the sizes of relevant systems. Turns out, for animals ranging from mice to elephants, the amount of food they need to stay alive results in an almost straight line when plotted against body mass. If we use the number of registered patents to model the creativity of people living in different cities, then again, the number of patents results in an almost perfect straight line as a function of the population of a city. And finally, plotting the assets and incomes of publicly traded companies as a function of the number of their employees, again, organizes the measurements in approximately straight line. What is going on here? All these systems are what we call complex adaptive systems. Such systems, by definition, are very difficult or even impossible to predict their behavior simply by looking at their individual components. And yet, here we are. If you look at each one of these systems as a set of living individual cells, citizens, or employees, the emergent behaviors are lining up in an almost perfect straight lines. And again, the common denominator in all these cases is the horizontal axis, the size of the relevant system. It means that some interesting insights can be discovered just by looking at the size of a system. This was Professor West's goal. He wanted to analyze these observations, how systems respond to changes in size, and what we can learn about them by playing with their sizes. As he put it, viewed through this lens, cities, companies, plants, animals, our bodies, and even tumors manifest a remarkable similarity in the way that they are organized and function. Now, at this point, you might be asking, well, that's definitely interesting, but this is a software design conference, software architecture conference. When I'm going to be back to my work next week, what am I going to do with all this stuff about cities and organisms, right? Well, that book doesn't mention software design at all, but all this stuff has so much to do with our job. These universal laws of growth, innovation, and sustainability mentioned in the title of the book, they apply to not only to these systems, but to a more general kind of system that the author called an energy supply network. As you're going to see a bit later, software design is an energy supply network as well. So that's our agenda for the next, I have 35 minutes. Let's see. So I'm going to start by exploring what are these energy supply networks and what makes them so special. Then we'll see how that theory applies to software design and ultimately how we can use it to manage complexity of software systems. Overall, you're going to see that the same laws of physics that govern the growth of businesses, cities, and organisms are the same laws that limit growth potential of software systems. And in the process, we are going to consult Galileo Galilei about why some code bases degrade into big balls of mud, and discover how this little acronym here, S-D, can tell us lots and lots of important information about software design decisions that we are making. So, what are energy supply networks? Stated simply, energy supply networks are systems that are sustained by the transport of energy through hierarchical branches of its components. In one way or another, the energy is extracted from the environment of the system and it's transformed to its nodes, the components of that system. Such systems are everywhere. Almost all aspects of our lives are controlled by energy supply networks. The simplest example is you yourself. You are an energy supply network. There you breathe, the food you consume, the coffee you drink. It is all energy that our body uses to power itself and to eventually produce code. Same is true for other mammals, except for code, of course. Mammals, animals, plants, and all living organisms. They are all energy supply networks. Typical example of human-made energy supply network is a city. A city provides water, electricity, communication, transportation, and other infrastructural services to its citizens. Just like a living organism, a city provides an energy to its citizens. Now, organisms and cities are kind of more physical energy supply networks, but they can also be more conceptual or virtual. For example, a company has to deliver energy in form of wages to its employees, and it also controls how information flows across the company, across its employees, across different departments, managers, CEOs, etc. How that information flows determines how effective that company is, whether it will be able to achieve its goals or not. So all these are examples of complex adaptive systems. They're composed of enormous number of elements, and the behavior of the overall system results from the interactions between all these components. Again, we cannot predict how the system is going to behave just by looking at one of its components, but that said, according to Jeffrey West's research, all energy supply networks are governed by same physical laws. So, if we could define software design as an energy supply network, we can use those insights to make better design decisions. So let's start there. Let's see what makes software design an energy supply network. And the main question we have to answer here is, what is the energy that is supplied by software design? What do you think? When we're designing, let's say, microservices, business processes, objects, what is the virtual energy that is transmitted across their boundaries? Information? Other?
Human resource.
Sorry?
Human resource.
Human resource. Yeah, that is going to be replaced soon. Yeah. Dependencies, yes, you're very close. Anybody went to Diana's talk yesterday? Knowledge, yes, that's knowledge. Exactly. When we build software, what we're doing? We're designing elements such as services, modules, objects, methods, etc. All of them have boundaries. And those boundaries, what are they doing? They're encapsulating some of the knowledge within the boundaries of a component, and they're letting some of the knowledge to go across the boundaries and be shared with other parts of that system. Now, the way two components are integrated, or the amount of knowledge that is shared across their boundaries, has a profound effect not only on the design of the system, but how that system will be able to evolve in the future, or how painful it will be to evolve it in the future. The more knowledge is shared, the more often components will have to change together. In other words, let's say that we are sharing a high amount of knowledge. That means that there is very high likelihood that some piece of that information, of that knowledge, will change in the future, and that change will have to be reflected in other components that are also aware of it. So there will be cascading changes. Now, how do we evaluate the amount of knowledge shared across boundaries? I don't know. I don't even know what is the unit of measurement we should use to measure knowledge, right? So instead, we can do something else. We can categorize knowledge in 4 basic types: intrusive, functional, model, and contract. Each one of these types shares significantly more or less knowledge than other types. Let's go over them quickly. Intrusive coupling. As the name suggests, intrusive coupling is about knowing something that you shouldn't know, and then using that for integration. In other words, let's say that you're working on a microservices-based system, and we know that we have to go through a microservices public interface. We are looking at it and say, whoa, what a cute user interface, but I have a better idea. I will go directly to your database, take whatever I need, maybe even change something, because why not, I'm already there, and that's how I'm going to integrate. Or maybe you're working on in an object-oriented language, and there is some external object that you're working with, but some of its methods are private. So what can you do? We can use reflection, right? Reflection is there for a reason, probably, so let's use it. Well, it was private for a reason. We are reaching out, we are working with it, we are introducing an intrusive dependency. Needless to say that such integration method is fragile and implicit. The author of that object is probably not even aware of that integration taking place, and we have to assume that any change that will be made to the implementation details of that module is very likely to break the integration and cause cascading changes in all the dependent components. With this method, we have to assume that all knowledge about how one of the components of the system is implemented, all that knowledge is shared across its boundary. Next one is functional coupling. Here we're switching from how a component is implemented to the knowledge of what is being implemented by that component. Those functional requirements that are being implemented by it. The practical implication is what we have here is multiple components sharing the knowledge of business requirements. When those requirements will change, well, guess what? The 2 components will have to reflect those changes. Take an extreme example. Let's say we have two modules that duplicate some business rule. Business rule changes. If only one of them is modified, then the two components will make conflicting decisions for the same input. As a result, the system will be in an incorrect state. So this level is also quite implicit because it's really hard to track those dependencies. Next one is model coupling. If you're into domain-driven design, well, I don't need to tell you about the importance of evolving models over time. So with this level, we have multiple components sharing the same model of the business domain. They're based on the same model. When we'll have to evolve the model, guess what? Again, we'll have to change them together. As I mentioned, if you're into domain-driven design, you know how important it is to evolve models. If not, I guess you know what book you should read to get into domain-driven design. And finally, we have the lowest level of shared knowledge, and that's construct coupling. Think about it as a model of a model. Here we have an integration-specific model that encapsulates all other types of knowledges. It doesn't let out any knowledge of functional requirements, of the models that are used internally, or any other implementation details. All those changes can be done within the component, and the vast majority of them is going to be contained by the integration contract. The integration contract will be much more stable than all those other types of knowledge. In DDD, typical example of an integration contract is published language. Outside of DDD, we have facade, we have data transfer objects. You can even look at API gateways as a way to introduce an integration contract that encapsulates how APIs are implemented internally. So now we can say that software design is an energy supply network. Components are sustained by the transport of knowledge through their hierarchical networks, different types of boundaries. These boundaries are like pipes through which knowledge is transferred across a system. So now we can leverage the insights from energy supply networks and see how we can use those laws of scale to design better software. Let's start by talking about how energy supply networks grow. And the thing is, organisms, cities, companies, and overall all energy supply networks, all of them tend to grow over time. Why? What makes growth so attractive? At the beginning of the presentation, I show you these three graphs that show how complex adaptive systems scale, how they react to changes in size. However, I purposefully omitted an important detail. These straight lines make it easy to assume a linear dependency between the quantities. For example, in the case of metabolic rate, it's easy to assume that a change in the size of an animal is going to result in a proportional change in its metabolic rate. That's not the case, of course. If you look closely, the two axes of each graph are logarithmic. Both horizontal and vertical values increase by factors of 10. If we were to plot this data linearly, then we would have elephants here in the middle and the rest of the animals here in the bottom left corner. The logarithmic scale allows us to plot wider ranges of values on a more compact area. Now, if we focus, however, on this chart, the right one, the one that doesn't use the logarithmic scale, we can spot an interesting behavior there. The metabolic rate grows as the 3/4 power of body mass, meaning it grows sublinearly. It grows slower than any linear function. Let's see what it means. Say we have these 6 dogs of different sizes, and I pick them in such a way that each next one is going to be twice as heavy as the previous one. Starting with Chihuahua, 1.8, Yorkshire Terrier, 3.5, all the way to Newfoundland that can be 58 kilograms. Now, let's ask, what is the basal metabolic rate of these dogs? What is the minimum amount of calories a day they need to sustain their body functions to stay alive. Not playing, not running around, just chilling, relaxing, comfortable temperature. What is the energy they need for that? Well, for Chihuahua, it's 110 calories a day. Yorkshire Terrier, twice as big, so it's probably 220. Twice as much for a pug, beagle, boxer, until we get to Newfoundland that needs whopping 3,500 calories a day. This linear thinking, it definitely sounds logical, sounds reasonable, it's easy to explain, it's easy to understand, but the only downside is that it's wrong. It's wrong because metabolic rate grows sublinearly, meaning for every doubling in size, the metabolic rate grows only by 75%. As an organism becomes bigger, it becomes more efficient. And it's especially evident here in the case of Newfoundland. It actually needs 1,474 calories and not 3,500 as we would have think by following the linear thinking trap. And of course, these sublinear growth dynamics are not unique to dogs or organisms. They can be observed in all energy supply networks. For example, here are the results of a study that investigated how many gas stations are needed in cities of different sizes. This one is from Germany, but the dynamics are the same everywhere else. Furthermore, it's true for all other infrastructural networks of a city. For every doubling in size, the city will need only 85% more roads, electrical wires, water pipes, etc. Now let's look at a similar and yet different growth dynamic. For that, let's examine the graph of registered patterns in cities of different sizes. Here again, it's easy to assume linear behavior. And again, we have logarithmic scale on both axes. And again, if we plot the same data linearly, we will get a non-linear behavior. Here, however, it goes in a different direction. Here, the number of patterns scales as the 1.15 power of the city's population, meaning that the number of registered patterns scales superlinearly, faster than any linear function. The explanation behind this is that as city becomes larger, it provides more opportunities for interactions, it allows a more diverse set of ideas to be generated, and as a result, the creativity of the overall city becomes more efficient. So again, if we take a city, double the size, the number of patterns will grow not by 100%, but by 115%. So these are the economies of scale. As systems grow, linear growth is actually very rare. In energy supply networks, most attributes grow either linearly, superlinearly, or sublinearly. So, going back to our topic of software design, we can say that the larger a software system gets, the more functionality we add into it, the less knowledge has to be added to implement that additional functionality. You can build up on the existing infrastructure, existing models, or you can use portions of existing functionality. Speaking in the language of growth dynamics, while the system's functionality grows linearly, the knowledge we have to add into the system, it grows sublinearly. Now, this notion of growth-driven efficiency bonus begs the question, if growth is so awesome and it's so beneficial and everything becomes so much more efficient, then why don't energy supply networks grow forever? Right? Why don't we see dogs reach sizes of dinosaurs or even Godzillas? Well, this question was answered all the way in 1638 by Galileo Galilei. In his last book, Two New Sciences, he says, you can plainly see the impossibility of increasing the size of structures to vast dimensions either in art or in nature. Also, it will be impossible to build up the bony structures of men, horses, or other animals so as to hold together and perform their normal functions. For if his height to be increased inordinately, he will fall and be crushed under his own weight. To illustrate his idea, Galileo proposes to think about a wooden beam. If we are going to scale it to twice its size, its weight is going to be increased in 3 dimensions. It's going to be twice as wide, twice as long, and twice as tall. Overall, its weight will be increased 8 times. However, the beam's resistance to fracture is defined by its cross-sectional area, which depends only on the width and height. As a result, this one is going to grow only 4 times. So if we try to do the same with, let's say, a human, let's say we want to imagine what's going to be if a human reaches the height of 4 meters, well, the weight will be increased 8-fold, while the limb's resistance to fracture will be increased only 4-fold, meaning that beyond some certain height, the person's joints won't be able to withstand the stress, and the body will just break under their own weight. All these are impossible. All these, Galileo 400 years ago explained why this is not possible. So, the different rates of growth is the reason why systems cannot grow indefinitely. When stress-inducing factors grow faster than stress-withstanding attributes of the system, that relationship limits the system's growth potential. In more general terms, we can say that when a system grows, it becomes more efficient, but the undesired consequences of growth become more efficient as well. What about software? Let's see what growth limits affect us. You saw that when the functionality of a system is expanded, the knowledge that we need to add into the system, it grows sublinearly, right? Well, let's see that in action. Assume we have a system here, and then we implement some basic functionality, and then we extend it a bit, add another feature, and then some stakeholder says that we urgently need to add another feature and one more, last one, and here we are. And now, have you noticed what is going on here? Well, all these lines describing all the possible interactions between the components of the system, they're growing superlinearly. Let's see this again. The knowledge we add, it grows sublinearly, but the interactions, the possible interactions between components grow superlinearly. Let's add this observation to our chart here. Now, there's one other thing we have to discuss on this graph, and it's this brown horizontal line. There is something that doesn't scale at all. What is it? Give me some ideas. What can it be? Sorry? Yes, exactly. Our intelligence. I'm optimistic here, right? I said that it's static. Studies show otherwise. But let's be optimistic. Let's say that it's static. So yeah, that's our cognitive limit. It doesn't scale, and we can expand the system until we are not able to cope with the complexity produced by the possible interactions of the components of that system. Once we reach that threshold, that system becomes, guess what? Big ball of mud. And from that point on, we start advocating that it should be rewritten from scratch. And of course, this time, we are going to design it perfectly, right from the get-go. Paraphrasing Galileo, again, that software system broke or crushed under the weight of its complexity. So what can we do about this? How can we extend growth limits because other energy supply networks are able to do it. Let's see how they're doing that. And here again, the answer was given 400 years ago by the same guy, Galileo. In the same book, he says, I have sketched a bone whose natural length has been increased 3 times and whose thickness has been multiplied until for a correspondingly large animal, it would perform the same function which the small bone performs for its small animal. So what he says here is that in order to extend the growth potential, we have to adapt the system's shape. We have to change the shape in order to make it support the vastly increased stress. Furthermore, he provides another option. He says if one wishes to maintain in a great giant the same proportion of limb as that found in an ordinary man, he must find a harder and stronger material for making the bones. So, to summarize, we have 2 ways of extending a system's growth potential. First, we can adapt its form, or we can use more efficient materials. Either way, sustainable growth requires innovation. Something has to change. For example, if we're looking at cities, one of the most important factors limiting growth potential of a city is overcrowding. But what does it mean, overcrowding? If you look at this historical data, as you can see, up to 18th century, the largest cities on Earth were up to 1 million citizens, but then suddenly, a century later, this graph skyrockets. Something happened there in that area. What happened there? Well, yes, we started innovating. Yes, industrial revolution, yes. And these innovations had changed the fundamental rules and opened new growth opportunities. So, going back to software, what kind of innovation can be used to extend growth limit of software systems? Our first option is to find a stronger material. Since our core problem here is cognitive abilities, if we can find software engineers with higher cognitive limit or growing cognitive limits, problem solved. Unfortunately, it looks like we're on the way there, but we are not there yet. So that gives us the opportunity to discuss the second option. So for now, for the observable future, we have to talk about another way to cope with superlinear complexity. And our second option is to evolve the form, the shape of the system, to reshape it in a way that will help us to manage the complexity. What is that shape? Going back to Jeffrey West, he says, highly complex self-sustaining structures, whether cells, organisms, ecosystems, cities, or corporations, require the close integration of enormous numbers of their constituent units that need efficient servicing at all scales. And this has been accomplished in living systems by evolving fractal-like, hierarchical, branching network systems. Don't know about you, but when I saw fractals for the first time, I was hypnotized. I was fascinated by this, by the simplicity, beauty, elegance. And it was in school, and when the teacher told us that fractals are everywhere in nature, I started to look for them everywhere in nature. Couldn't find them. Well, turned out these psychedelic patterns are only relevant for mathematical fractals. In nature, fractals behave a bit differently. Let's say that we're looking at broccoli. That's the most common example of fractal geometry in nature, but you can divide it only like 4 or 5 times until it loses its self-similarity. So these fractals, mathematical fractals, belong to mathematics. In nature, what we have is fractal topology of networks. And these fractals are really everywhere. Here are a few examples of rivers from Google Earth. As you can see, the branches of these rivers are not exactly the same at all scales. However, in the way they are branching, they are self-similar across all scales. And the same can be observed in the way that energy is delivered in animals, plants, and almost all living organisms. Now, doesn't it all sound familiar? haven't we already talked about all these examples, but in some other context? Actually, we have, yeah. Remember that some aspects of energy supply networks grow sublinearly, slower than any linear function, like metabolic rate of animals, number of gas stations, roads, electrical wires, etc. Well, almost in all cases of sublinear growth, there is an underlying fractal network that actually optimizes the efficiency of the flow of energy in that system, and that fractal topology enables these systematic savings. So in our case, in software design, we can exploit this fractal-based optimization strategy to manage complexity. Ideally, we can turn this complexity function into a sublinear one. That's a good goal to strive for. Not sure it's possible, but let's be optimistic. Anyway, let's see how we can at least manage that function of complexity, how we can reduce it over time instead of letting it go crazy and grow superlinearly. For that, we need fractal modularity. So software design is an energy supply network. It delivers knowledge. The way modules are integrated, it defines the amount of knowledge that is going to be pumped through the system, across the system. As in biological and other energy supply networks, the modules are hierarchical. A module can have multiple internal modules and so on. Now, what we need here is a self-similarity principle that can be applied at all levels of abstraction, at different scales. So let's see how we can define it. You saw that modules are sharing knowledge. There are 4 types of that knowledge, and let's call that model that scale integration strength. The higher the strength, the more knowledge is shared. Another important property of a connection or coupling between any 2 components of our system is the physical distance between them. The thing is, we can observe coupling across methods, objects, services, systems belonging to different companies, etc., different physical distances. And the higher that distance is, the more expensive it's going to be to change both coupled components simultaneously. So we can say that the cost of changing 2 coupled components depends on the distance between them. The higher the distance, the more effort we'll need to invest in order to implement the change. And now that we have these 2 quantities, let's see their extreme combinations, and let's see what we can deduce from that. So let's start with high distance and low strength. So on the other hand, we have high distance, which means each change is going to be expensive. Lots of collaboration efforts will be needed to implement it. However, it is balanced by low strength. We are minimizing the knowledge that is shared. That means that we're minimizing the number of such cases in the future, the number of such changes in the future. So overall, this relationship describes what we usually call loose coupling. Now, the opposite, high strength over low distance. So let's say that we have 2 components, we are observing that they're sharing lots of knowledge, and we are trying to refactor it to a lower level, but we can't. We can't because of business requirements. We have to share knowledge of functional requirements, and there is nothing we can do about it. Okay, so we have 2 components that will have to co-evolve. They will change together. On the one hand, it sounds not that good. However, that is balanced by low distance. The components are located close to each other, so we won't have to invest lots of effort to implement those changes. So overall, this relationship is what we call loose coupling. High cohesion. That is high cohesion. Now, what about that one? Low distance and low strength. That's the tricky one. Is it a good one? Is it a bad one? A bad one? Okay. 2 hands. Wow, I hope you are not in coma or something. Yeah, so that's a tricky relationship because if we have two components that are not sharing much knowledge between them and located close to each other, who cares? Only two of them. But once we are talking about larger numbers, let's say 15 or maybe hundreds of such components, then what we have is a bunch of unrelated stuff shoehorned into the same boundary. When you will need to evolve something in that boundary, you will have to make your way through all those unrelated components, and that's cognitive load, which results in complexity. So this combination increases complexity, or what I call local complexity. Complexity within the component we are working on. And finally, we have high distance and high strength. And this relationship, who thinks it's a good one? Just kidding. That's world of pain. That's one way to describe it. Lots of cascading changes. Each one is going to be expensive to implement. I call it global complexity because it increases the complexity of the overarching system. So say we are working on this component, and we are introducing complexity in the overarching system. We are doing a great job. So we have 4 quadrants. We have 4 options. Where do you want to be? I asked this question at one conference, and the answer I got was, I want to be on red squares because of job security. If that's something you are interested in, you know how to do it. That's how you can make some mess, some serious mess. If instead you want to manage complexity and you want to avoid complexities, stay on the green squares. And these green squares mean that modularity is inversely proportional relationship between knowledge that is shared and the distance that is traveled by that knowledge. We can compact this function even a bit more, S caret D. Now, how to apply it in day-to-day work? Well, first of all, always minimize the knowledge that you're sharing. Find that minimal level that you need to share, and you cannot do anything about it. Once you're there, balance the distance. Both are high, minimize the distance. Both are low, increase the distance. And most interestingly, in my opinion, apply this at all levels of abstraction. Because if you're looking at different types of boundaries, what is considered an integration contract here will become model coupling on higher levels of abstraction and even implementation detail on even higher level of abstraction. So these levels, they are not absolute. They depend on the level of abstraction you are working on. They're all relative. So this is our fractal geometry. This is the self-similarity we have to enforce on all levels of abstraction to optimize how knowledge is flowing across our systems. I have read 0 here, which means I have to wrap up. But before I do, I have a tradition. And you are going to take a part of it. Say hi. Thank you. OK, so quick summary. Energy supply networks, as they become bigger, they become more efficient. That's our self-similarity principle. I wholeheartedly recommend reading this book. If you're going to read it, you will see that I cut some corners here. There are some criteria that have to be met by a system to be considered energy supply network. It's your homework. See how it applies to software design. If you want to learn more about coupling, well, that's another book I can recommend. That's my moment of shameless marketing. I also build a website, coupling.dev. You can see some summaries there. And of course, links to purchase both of them, coupling and learning domain-driven design. And with that, I cannot speak that fast anymore. Thank you so much.